Our next problem is also very interesting GP problem. We are given with if a plus b plus c is equal to x times b, where a, b and c, these are three distinct real numbers which are in GP, then we need to find the range of values of x in order for this expression to be true. Now a plus b plus c is equal to x times b. So we write this as a plus c equals x minus 1 times b, or b is equal to a plus c upon x minus 1. We remember this thing because it may be useful after some time. Now we know that a, b, c are in GP, hence b square equals ac. Now substituting the value of b as a plus c upon x minus 1 in this expression, we get a plus c whole square upon x minus 1 whole square is equal to ac. On further simplification, we get a square plus c square plus 2ac is equal to ac into x minus 1 whole square, which gives us a square plus ac times 2 minus x minus 1 whole square is equal to plus c square is equal to 0. Now dividing both the numerator, or in fact dividing the whole equation by c square, as c is not equal to 0, we get a by c whole square plus a by c times, this can be written as 1 minus x square plus 2x plus 1 equals 0. Now very clearly this is a quadratic in a upon c, so putting a by c equals t, we get t square plus t times 1 minus x square plus 2x plus 1 equals 0. Now a, b, c are three distinct real numbers in GP, so a is real, c is real, so t has to be real. So this is a quadratic in t. In order to be for t to be real, we need discriminant should be greater than equal to 0, which makes 1 minus x square plus 2x whole square should be greater than equal to 4. That is 1 minus x square plus 2x should be greater than equal to 2, or 1 minus x square plus 2x should be less than equal to minus 2. This equation becomes x square minus 2x plus 1 should be less than equal to 0, and we know that this is a perfect square, and a perfect square can never be less than equal to 0. The only possibility is the perfect square can be equal to 0. So on putting x minus 1 whole square to be equal to 0, we get x equals 1. But we know that a plus b plus c is equal to x times b. X equals 1 means a plus b plus c equals b, which gives a plus c equals 0, or a equals minus c, which is totally rubbish because b square is equal to ac gives ac is positive, hence a and c should have the same sign, and here it is given that a equals minus c, so this is totally rubbish. So x cannot be equal to 1. This equation gives us, taking the second equation, we get x square minus 2x minus 3 should be greater than equal to 0, which gives us x plus 1 into x minus 3 to be greater than equal to 0, which gives us x is greater than equal to 3, or x is less than equal to minus 1. But one thing we should remember, that t square plus t times 1 minus x square plus 2x plus 1 equals 0. If the discriminant of this equation is equal to 0, this means the equation has equal roots, and since the product of roots is equal to 1, so either the roots will be equal to 1 and 1 or minus 1 and minus 1. Since the roots are equal, on putting the discriminant equal to 0, but the t which was equal to a upon c, it cannot be equal to 1 because a cannot be equal to c, as these are distinct terms of a GP, and t equals a by c cannot be equal to minus 1 because a cannot be equal to minus c, considering the fact that b square equals ac gives ac to be positive. So a and c should have same signs. So discriminant can also be never equal to be 0. So the discriminant of this equation always has to be greater than 0, strictly positive. Hence x has to be strictly greater than 3 and strictly less than minus 1. So the results which we got earlier, those were x greater than equal to 3, so removing the equality sign, and x less than equal to minus 1, removing the equality sign from this as well, we get the final answer as x greater than 3 and x less than minus 1, which is our final result.